Hello everyone. We are at a point where the drain current is a linear function of VDS, and this ensures this particular condition VDS less than equal to VGS minus VT ensures that your device will operate in a linear mode of operation, and the drain current for that will be given by VGS minus VT, VGS minus VT into VDS. This is the drain current equation. Okay, so what we have to do is we have to actually see what is the impact of VGS and VDS on the drain current when we try to vary both VGS and VDS, and what is the impact on the drain current. We need to find out that, because there might be applications that will be working at lower voltage of VGS, and there will be applications where your device is operating at higher voltage of VGS. So we need to actually simulate and find out how your device will behave with these different voltages, with different voltage levels. So we have identified a few of them. For example, let's do it one by one. We have this VGS. Let's try to switch the VGS from 0 to 2.5 volts at an interval of 0.5 volts. So for example, we'll take different values of VGS, which is 0.5 volts, 1 volts, 1.5 volts, 2 volts, and 2.5 volts, and see how does the device behaves at each and every values of VGS. Okay, so in this particular scenario, what should be the value of VDS? Till what point your device will be in a linear mode of operation? And the answer is VGS minus VT, which is clearly specified over here. So VDS should be less than or equal to VGS minus VT for your device to be still operated in a linear region. Okay, so in this case, in this particular scenario, you can sweep your VDS for, let's say for a situation where you have VGS equal to 0.5 volts, you can sweep your VDS from 0 to 0 to 0.05 volts to make this device operate in a linear region of operation. Okay, similarly, you can sweep your VDS to 0 to 0.55 volts to make this device operate in a linear region of operation, because right now we are focused only in a linear mode of operation of the device. Okay, you can still sweep your VDS from 0 to 1.05 volts to make this device operate in a linear region of operation. So at every values of VDS, at every values of this VGS, you will have different values of VDS to sweep to still make this particular device operate in a linear region of operation. And we will be very soon doing some calculations in using this particular model. Okay, similarly, for this particular condition, you have your VDS can be swept from 0 to 1.55 volts, and for this one you can sweep your VDS to 0 to 2.05 volts. Okay, so it's not very feasible to calculate the drain current for each and every combination of this one, because it will take ages for me to do so. So what I will do is I'll take, so the question that I have to answer at this point of time is, how do I calculate the ID at different values of VGS, which we just put it over here, at different values of VGS, and at every value of VGS we want the VDS to be swept till 0 to VGS minus VT. Okay, and still identify the drain current using this particular linear equation of drain current. So how do I do that? Because doing it manually will take me ages to do it, and I need some engine that has got this even more accurate models than this one to do the calculations. And for that, what we'll do, we'll move to Spice. We'll do some Spice simulations. We'll give some, there is a way that you can give the circuit to the Spice along with these conditions that we just specified, and the Spice engine will do it for you. Okay, so that's the one introduction to Spice, where this is the way how you feed your inputs to the Spice simulations. So basically, there is a way to tell the tool that you sweep your VGS from 0 to 2.5, you sweep your VDS from 0 to VGS minus VT, and then give me the drain current equations, give me the drain current waveforms. So there is a way to do that, and that we will be doing in Spice simulations. But before entering into Spice simulations, we have to answer one more question, that what happens when your VDS exceeds VGS minus VT. That's a very important question to answer, and that's where your device enters into the saturation region of operation. So what we'll do is, we'll start with the new topic, saturation region of operation, in the next video, because this will take some bit of time and some bit of theory to understand. And once we are done with the saturation region of operation, we'll move to simulations using Spice. Okay, so let's try to do all this in the next video. Thank you.